Okay, please welcome Sabrina Gonzalez Pasterski, and she'll tell us about when HPS meets AMPS, how the software dissolves the firewall. Over to you.
Thank you. So thanks for the introduction, and I'm really happy to be here because especially coming from more of like the soft physics story, it's nice to be at UCSB for the AMPS story started. So today, let me get to this topic of the talk. What I want to present today is a recent paper with Herman, titled the same as the talk, where we're trying to provide a soft physics interpretation of some of the ways to avoid the AMPS Firewall Paradox. So let's set up what I hope to talk about today. From the point of view of, say, studying asymptotic symmetries of asymptotically flat spacetimes, you notice even without any horizon business going on, that the infrared physics is pointing to an infinite dimensional enhancement of Poincare rate. So you have these large sets of symmetries which govern scattering, and one interesting thing pointed out by Hawking, Perry, and Strominger was that these extra symmetries should also constrain scattering in the presence of black holes, also constrain black hole evaporation, etc. So the key point of that story that we're going to take away from it is that these black holes have soft air. Now, what can we do with it? So throughout the talk today, my hope is to try to introduce how the soft air phase space associated with the horizon can be used to evade the firewall paradox in the following sense. So what I'll mean by the firewall paradox for us is this tension between the fact that Hawking radiation and smoothness of the horizon would tell you that you should continue to generate new entanglement with between the black hole and its surroundings, and then the issue instead of, because you have this finite size system, that eventually the von Neumann entropy should decrease. So how do you reconcile the fact that monogamy of entanglement would tell you that perhaps you don't have the right entanglement to have this smooth horizon? So what the goal for this talk today is to basically give a Hawking, Perry, Strominger style interpretation of some of the modes that have been used to basically provide a protocol that would reinstate the standard smooth horizon. So basically, connecting the two stories is the goal of the talk, and using machinery that already exists from the point of view of how to address the AMPS firewall paradox, but now giving it a soft hair interpretation. Great. So big physical question that's like on our minds is, how does soft hair affect the experience of an observer falling into the black hole? And this is nice because it's in contrast to some of the previous work following from Hawking, Perry, and Strominger, which is more, how do you count, say, degrees of freedom, like the actual like entropy counting of the Sven horizon using soft hair modes, or resolving information paradox. Say you've evaporated the black hole completely, now you have this Hawking radiation, it's the thermal state that's in conflict with the fact that we expect the S matrix to be unitary. And Hawking, Perry, and Strominger at one point had proposed that you're really just not measuring the soft modes that are entangled with it, and if you took the soft hair into account, that could resolve it. But we're trying to address a slightly different question, which is again this experience of falling through the black hole horizon. Good. Okay, so the goal for this talk is the following set of 4 points. The first part of the talk is going to be making some claims about the structure of the soft hair phase space, and then we're going to start using that to then talk about the experience of an infalling observer. So part 2 will be to explore the entanglement between the observer that's falling in and these soft hair modes, motivate that when you fall in, you're measuring the soft hair, at least some fraction of it, and then demonstrate how basically you can now provide this HPS style soft hair mode interpretation of different qubits appearing in quantum circuit technology that would allow you to evade the firewall, as presented, say, by Benny Yoshida and collaborators. So the first part of the talk is again about this soft hair phase space and basically some of the distinctions between maybe how we're treating it compared to Hawking, Perry, and Strominger, but it's in the same spirit of theirs. We make the following claims about soft hair degrees of freedom. So within this, like the set of claims, I guess they go from being, let's see. So like charts 2 and 3, I guess, are the first ones I'm going to focus on. But in essence, we want to say that the soft hair modes that you're measuring are essentially associated with the horizon, but that you don't necessarily measure it unless you've fallen in from infinity and basically set your coordinate frame. We want to think of them as being some sort of like classical feature of the space-time that the observer is experiencing. And then we will show that they're actually very sensitive to matter falling into the black hole, as we'll capture with some commutation relations of the phase space associated with this horizon. And then the assumption that they carry a large amount of entropy is what's going to allow us to use the existing quantum circuit technology. And then this notion of measurement is going to be applied the last two features of the software. Good. Okay. Oops. Let me. Okay. So what I want to now say is that there's various coordinate systems we're going to be using to describe the black hole. So in the first case, what we have is the following. We have, say, future and past null infinity. And if you want to use advanced or retarded coordinates, let's take this form. So for instance, in advanced Bondi gauge, we have the simple form of the metric. Meanwhile, if you're in the near horizon region, you can also switch to Kruskal-Sekker's coordinates. And we're going to consider linear deformations, diffeomorphism of these this background Schwarzschild metric. So they take the following form. So near past null infinity, we want to stay in advanced Bondi gauge. So the super translations, which are basically performing an asymptotic symmetry analysis near past null infinity, will give you the following set of symmetries of the metric as it falls off near past null infinity. And so acting on the metric, you get this change here. So, right, we've taken our flat metric and now we have this F-dependent diffeomorphism of past null infinity. And also at like r equals 2m, you see how it shifts the horizon. So you can do the same thing in the UV coordinates and it'll take a slightly different form. But what I want to emphasize is the following.
Sabrina, can I interrupt, please?
Yeah.
Are you assuming the Bondi coordinates are good all the way to the horizon?
No, I see. Okay, so I noticed if you notice me with a surprised look on my face, it's because I had one version of the slides where I'd slightly arranged things a little bit, hopefully cleaner, and this is taking a step back, but I'm fine with it. So I'm gonna the ordering is slightly is the old version of part of it. As far as the old version, what I want to argue is the following. So let me just jump to these pictures here. So in the point of view of the Hawking-Perry and Strominger papers, what you have is you have they do extend, like they're looking at the black hole horizon in the same coordinate patch as past null infinity. And for that, it's so like the issues you really have like say 3 patches. You have this patch near past null infinity, say, that I guess you can consider extending here, but definitely for future null infinity, you need to be wary about going from U to V. But what I want to argue instead is that really this phase space, you should be doing an asymptotic symmetry analysis or near horizon analysis of the appropriate residual symmetries. And that's like what Laura Donnet and other, Bob Wald and others they're studying these, the near horizon degrees of freedom in that soft phase space. So what is, what's happening for us now is we want to convert is the following, like so in this last slide here, right now, I am describing the same metric in either these advanced retarded coordinate or advanced coordinates near the horizon, near the future horizon, or Kruskal-Sekker's. But I want to basically be able to connect the story of in advanced Bondi gauge that have been studied. We're trying to move it away from and put it in just a coordinate patching between.
Oops, I think she cut out, yes?
Yes.
Oh.
Sorry, we lost
okay.
you for a moment there.
Oh no, this is the internet connection issue that I was worried about. Okay.
Yeah, you're back.
Okay, so I am back. Hopefully I'm back. I need to look at the video so I can see people. So my claim is the following. So all I'm trying to do right now is to connect expressions that have been computed in, say, advanced Bondi gauge near the horizon to pushing that into a coordinate patching between near horizon coordinates and past null infinity. But I don't want to claim that the same here is this. It's that it's only a super translation that that you'd see at past null infinity. So, so here's the volume. The claim is that a lot of the near horizon analyses, I think like the ones of like Donnet and collaborators, we're still using the same coordinates as, or at least ones that were easily translated to the ones that Hawking-Perry and Strominger are using, which is using these V and R and S2 coordinates. So right now I'm just sticking to that language because like I'm comparing equations with the ones Hawking-Perry and Strominger, but I want to point out that there should in principle be different soft term modes associated with the horizon. Is that, I hope that we can be cutting out and me rambling a little. That's okay.
Yeah, I mean, are you doing this in a fixed background? I mean, are you picking like Schwarzschild?
Right now I'm on Schwarzschild, yes, sorry. So yes, right now, literally what I've set up is just on Schwarzschild.
Okay,
Sorry.
so for Schwarzschild.
I was so scared about my internet connecting that I swapped a couple slides out at one point, and and now I'm like remembering the old rearrangement, but okay.
Okay, so for just Schwarzschild, I can see you can relate things, but
yeah,
more general black holes with things happening in between, outside the horizon, it might not.
Exactly. And I'm gonna get to that a little bit later than maybe I'd hoped to, because I just completely was freaked out about. I opened up the document. I'm sorry, but like it's all the same stuff. It's just it's reordered a little bit. I'm like, so just remembering what I did. It's my bad. Okay, so what I'm saying now is that you can look at it in either coordinate system. And what I want to point out though is that essentially, if we wanted to say go to a metric where we've kind of eliminated the near horizon soft modes by basically just saying it's the way that you get around this, the fact that the black holes have no hair, is that you say that this hair is actually just diffeomorphisms essentially, but it's not actually fully a diffeomorphism. It's basically like NA given, say something falls into the black hole, then it's going to induce a super translation, say transition along the generators of the horizon. So if in some static time range, I can describe the change of this black hole by the soft hair by something that I could gauge away. Basically, I can always go to a gauge where it's the standard critical coordinates for that region, but when I go outside of the black hole, I need to eventually patch into the fact that there's this F dependence there. So basically, if I have my full space-time and I do a super translation, I want it to act everywhere. So all I'm saying here is that basically, if I look at null infinity, I'm going to see that whatever radiative processes are happening are causing me to have vacuum to vacuum transitions along past or future null infinity. So if I then have some sort of slice that goes to past null infinity and cuts through my black hole, typically with these soft hair modes associated with the horizon, if I globally do a super translation that acts on all of them, I'm going to either uniformize the black hole horizon or null infinity, but not both. But I can if I decide to use two different coordinate patches. So that was a little bit of a roundabout way to get to the point that this notion of the soft hair should be intrinsically associated with each of the boundary components of my space-time, and that I need to take into account the fact that I can actually change these soft hair degrees of freedom. So there's going to be two conjugate modes. So let's look at the fact that we can implant super translation here. If we just consider a shock wave going through, in this situation, it's going to be like a massless set of matter that satisfies the stress tensor being conserved, coming in from past null infinity and going up to the horizon. So what happens is that you have the stress tensor, and you can parameterize the stress tensor via the change you want to implement in the soft hair. And so this is following from Hockenberry and Strominger. They're giving some value f, which is a function in the S2, and saying that if you send in this shell of null matter, you will induce on the horizon a shift of the following form. So it basically is doing a super translation, but only for v greater than v0.
Can you remind me, is this spherically symmetric, or is this a generic angular dependence?
The point would be that it's not spherically symmetric.
Okay, so good. So the angular dependence is in what? In T hat or something?
So if I look at the night sky, the angular dependence is like a function of the coordinates on this S2.
No, what's it parameterized in? I guess it's in this T
hat. It's parameterized by my F right here. So Z and Z bar is what I normally use, but here, so A for me, I'm used to using A being like Z and Z bar, which are just like projective coordinates on the celestial sphere. Is that what you're asking, or just?
Okay. Yeah, no, it's the angular dependence is in the function F hat, I guess.
Yes, exactly. So I've kind of pushed things a little bit into just the fact that I've like used this F, but I want to point out now that yes, this F is really an arbitrary function on I guess the night sky you're looking at past null infinity essentially.
Yep.
Good. Yeah. Good. Okay. So there are, I guess, a couple points to point out. The one is that the horizon is shifted when you throw something in. So from the point of view of the fact that you have this arbitrary angle dependence, one should be wary of the fact that so the mass is changing because of actual the net integral S2 amount of energy that you've thrown into this black hole. So that's shifting the horizon overall. But the soft hair modes will also basically the horizon generators would shift locally at different points on surrounding the horizon. And so this F will capture that shift. So what I want to point out with this story is that essentially your like this back reaction will be nicely captured by the structure of the soft phase space. So what I want to point out in here right now is that essentially we've gone through the story where whoever had asked the question, I have like the videos off right now so I don't see, of whether or not you really expect to be using, say, just the description at past null infinity for this horizon. And so in the example studied by Almheiri and Strominger, sure, they do the simplest case of having some massless shell of matter falling through the horizon. And there you can kind of identify the fact that the super translation that was induced at past null infinity is the same as that at the horizon because of that, just the way that the matter is just falling through. But in principle, though, one can have other matter falling through the black hole, and one would still expect to, on the horizon, induce a similar shift in the super translation degrees of freedom. And that is not as obviously like one-to-one with whatever is happening at past null infinity. And the same thing you can imagine matter that fluxes, say, in the direction that my mouse is hopefully moving in your screen. And there you would also, again, expect that the structure of the soft modes at the horizon are not going to be the same or like quite identified with what's happening at one of the infinities. Good. Okay, so what I want to, I guess, capture out of what I said so far is that essentially, although I can move things around, so if I want to like describe some my near horizon geometry in a certain nice canonical way, if I need to take into account the soft terror in some way, and I do so by either saying that's how I glue between the near horizon geometry and infinity, or putting everything on the horizon using like the coordinates that Almheiri and Strominger do. And the point of that, I guess, exercise is just to point out that in some sense, if I decide that I'm falling in and I've set my my set of observers, rulers, and clocks to effectively pick a super translation vacuum from the point of view of past null infinity, when I fall through the horizon, I would basically be measuring this soft mode. So let me see. What is it? This one slide. So what I want to point out also here is that basically there's an F plus and F minus associated with every null boundary here. So at past null infinity, say, I would be basically able to induce a memory effect at future past null infinity, and the same thing at the horizon. So whenever I write Fs now, I'm going to be focusing on the modes associated with the horizon, but in general, super translations will shift everything. So let me just see one. Okay, good. I want to make sure the slide's still staying. It wasn't like there's something happening. Good. So before I guess, just do that degree of freedom counting, what I want to point out is you have this super translation symmetry, which is so that there's a level at which there's this overall diffeomorphism you can do on your metric, and that is shifting all of my coordinate patches by the same parameter F. When I do that, I end up having a ward identity for my S matrix. So the action on the in state is compensated by similar action in the out state. Basically, there's an invariance of my scattering process under super translations. So when I have a horizon, this is going to split into two different contributions, and we start seeing that the structure of the Hilbert space for the scattering process involves, say, an early radiation component, a black hole component, et cetera. So the actions of these symmetries, like, in some sense, tell you that you're like that you need to be a bit careful about ignoring, say, the presence of the horizon, even though you originally derived this word identity from soft theorems. What I want to now point out too is that these charges, when they act on each of these boundaries, are acting on both matter and on the gauge modes. So the soft part of the charge is going to be inducing a inhomogeneous shift in the metric, which is going to be captured by two modes that were parameterized by directions on the S2. So I use just Z because it's a compact notation, but I really mean Z and Z bar as far as like these are arbitrary functions on the S2, not holomorphic ones. The soft part of the charge is the one that's inducing the shift. And so it will change both the plus and minus asymptotic values along the horizon generators by some amount. So I can, if I convolve this with an arbitrary function F, that's like just a classical function, I reproduce the desired super translation that I want to do. But in principle, now the point is that this phase space is such that I have a future and past limit of my my operators that are parameterizing the zero modes of the metric. So now let's actually unpack that a little bit more. So what I have is the following. I have the following degree of freedom counting when I have or don't have a horizon. So I want to point out that in the original stories without the horizon, you have essentially a couple of things going on. So the statement is if I have some sort of inspiraling binary system or something happening in the bulk here, and it generates radiation, typically that radiation will induce a vacuum to vacuum transition. So within my metric, the part of the metric that is angular and just subleading to the round sphere metric will undergo a dynamical shift. So like literally this, like if I had just a charged particle accelerating, say the fact that it emits radiation because of the fact that it accelerated would tell me that my gauge field, for instance, would undergo a similar change. So here, if I have a bunch of test masses and then some radiation is emitted, they're going to be moved relative to each other. And the memory effect there is basically telling me that I am dynamically undergoing basically a vacuum to vacuum transition between two super translated vacua relative to one another. So along functional infinity, I have these basically two low energy degrees of freedom, because one of them is literally a zero mode and one of them is a shift. Now, I also have the similar structure at Pascal infinity, but the standard law is the following. So Strominger and friends would normally do an antipodal matching condition here, basically relating the data antipodally at the pass limit of future null infinity and the future limit of Pascal infinity. And if you then look at the phase space, that's basically knocking it down by 2. And then if you actually wanted to construct BMS invariant quantities, because everything then shifts together, one would imagine that that would also reduce the phase space. But if I now introduce, say, this horizon component, what I have is I have potentially, at least like according to this near horizon analyses, 2 more degrees of freedom. And if I wanted to similarly reduce it, I need to define some sort of matching near future time like infinity. But there, I think it would be harder to actually, like you can imagine having massive matter exiting at I plus here. And given that, one would probably not expect the same type of antipodal, like some sort of matching here in the same way that one would at spatial infinity if you assume some sort of regularity there. So I just want to point out that essentially, I think it's useful to think of the degrees of freedom associated with this horizon soft modes as basically augmenting the soft hair phase space that you have when you would otherwise not have it if you just had this Minkowski space structure. Now, eventually, if this black hole evaporates, then sure, you might say that you now return back to this future in Pascal infinity, and you notice that some of Strominger's papers following up on HPS look at the implications for the information paradox just from that point of view. But for what we're talking about now, I care about the fact that there is this horizon because I want to think about how these soft modes interplay with the observer's experience falling in. Okay, so one thing I can do, now I don't need to always consider states that are actually super translation invariant, but I can choose to look at operators which are invariant under super translations. So one way one can do this is to basically dress all of your operators. So if you have some sort of massive particle, you want to dress it with this soft graviton field. And so to do so amounts to, because the hard charge is already basically acting diagonally on the states that are that you define, the soft part, now you need to basically add a cloud back. So you can do this dressing by adding this basically Wilson line operator. And so what it is this phase that depends upon the metric component F. But I want to point out that it's a little bit more subtle in the sense that which F am I using? So we pointed out there's various Fs that appear. There's the future limit, say, of the horizon and the past limit of the horizon, as well as like basically where do you want to anchor it? Each of them will shift under super translation, so each of them will be effective to basically produce something that's going to be invariant under super translations. And the way yes.
So you've moved on to the issue of measuring the soft hair, but maybe before that,
yeah.
There's a question related to implanting the soft hair, and that is,
yeah.
Well, you could ask whether the soft hair really encodes all of the information inside the black hole.
Yeah.
So, for example, you could, well, you could ask for each quantum state of the black hole, do you have a unique soft hair configuration outside the horizon? I think you can generate examples that falsify that, because a very simple toy example is send a Morse code message in spherical waves into the horizon, and that's not going to encode itself at all in the software because you'll, by basically Birkhoff's theorem. But I think there are other more elaborate examples that you could come up with that argue that there are a lot of internal states of the black hole that are not evident in the profile of the soft hair.
Yeah.
And if so, then you can measure the soft hair all you want. You're not going to learn about those states.
Yeah. So I want to argue that I don't need the soft hair to include all. Like in the end, I'm only going to need it to include a large fraction. So like order 1 fraction of the information compared to I guess what could be in it. Now that might still be a bit of a bigger claim than maybe what you'd be comfortable with.
I think that's not enough to restore unitarity, basically, because as long as you can have internal degrees of freedom of the black hole that are, not encoded, whose information is not encoded in the soft hair, that information doesn't get out. And, by the way, another way that you encode information in the black hole is the buildup of the Hawking radiation. You have outgoing Hawking photons, they're particles, and they're entangled partners that go deeper into the black hole. And by the way, most of that is S-wave in typical situations. So most of that is spherically symmetric. It just, in matter of fact, when you have a, say, spherically symmetric black hole. And so there, that the profile of, what was emitted and the
but I mean, there won't be
internal
spherically
states of the
symmetric
black hole also you would expect not to be encoded in the soft hair.
So let's unpack a little bit for a given pair process, how are you inducing this? Like, I mean, at the level of maybe like say near the horizon, and I have this pair production going on. That's not spherically symmetric at the moment. You're like, there's something going between that and making an actual S mode because I have something locally happening at a point on the horizon.
No, if you think of the quantum particles near the being produced near the horizon, and again, it's an outgoing particle and its partner that goes into the horizon. You can always decompose that in terms of an angular momentum basis, and the dominant effect is in the S wave, and those are just S wave excitations coming out, or simply spherically symmetric excitations.
Sure, but what I want to argue is that so say you even just if you send something in that's so let's consider the problem of sending in this original shock wave that like Hawking and Strominger do, where they have this angle dependence. And it goes into the horizon, and then it's generating supposedly, for at least in my phase space counting, this change in F. Like it's literally inducing this change in the degree of freedom that I'm using to encode what's happening here. So how does the dynamics of this low energy radiation going out that's spherically symmetric, if that doesn't change then the software mode at the horizon, then why can't maybe my fear is the following, is like I'm slightly worried about the statements you're making about soft radiation, like all that eventual maybe hard radiation coming out that's spherically symmetric, not containing what I'm saying is intrinsically at this horizon with this soft hair mode. Do you see what I'm like? Let me try to phrase the problem in a like, to me, like so for you, I send something in that's angularly complicated.
You can do that.
And I'm saying right now that Hawking and Strominger say that at the horizon, it's then inducing this basically memory effect, say, of my soft hair modes.
Yeah, so it's not surprising that the gravitational configuration outside the black hole has some correlation with the angular profile going in. Yeah, that is not surprising.
Good. So then the question that you're asking then is like, then something is coming out that's spherically symmetric. But if anything, sorry, like I'm not sure if I'm not sure if that invalidates the point of view that there could be soft modes along the horizon that are kind of, I guess, capturing the angle dependence of things that are crossing it in a way that doesn't affect the fact that hard radiation is dominated in the low angular momentum.
Well, the unitarity problem is the problem that you end up with a lot of information in the black hole that doesn't get out. And how do we see that? It's because there are a lot of possible quantum states of the black hole that are correlated with the outgoing Hawking radiation. They're entangled, and that entanglement never makes it back out again. And so you might ask, well, is that entanglement really encoded in the soft degrees of freedom? Well, if you have many such internal states of the black hole, which are not evident in the soft modes, not correlated with the soft modes at all, then you still got the problem, I think.
I think the question, yes, so what's going to, So maybe we can try to eventually bring it down to where like the problems are in the assumptions of the circuits, that I am assuming that my soft modes are basically scrambled with the rest of whatever else is the code subspace of this black hole during its natural evolution. So I assume that I'm just trying to understand, like, so basically what I'm trying to understand is that fine, I'm fine with saying like you do some computation about like throwing something in or seeing what like hard radiation comes out, but I'm a little bit worried about in the very like the strictly IR limit whether or not it would make sense to say that I'm still imprinting some angle dependence.
Well, anyway, I don't want to derail you too far with this stuff. Anyway, I think that there's an issue here we might want to follow up on.
Yeah, no, I'd love to. No, I definitely would love to. I definitely want to understand, because I'm just like, I imagine I mean, maybe the very naive picture of just seeing like if imagine a Hawking pair was produced like at some point, say, and not jumping then to the computation of breaking it into angular momentum modes, which I'm fine with. Like that act to me would be like some very small change in the software at that point. So I don't quite see then how what maybe is like dynamically there's a disconnect for me right now to see how like that process, which seems like very much local on the horizon, turns into the statement of like find the hard radiation going out is strictly symmetric, but I don't know how that affects the soft modes right now. So I want to understand that better, and I'm happy to talk. Yeah.
Quick answer to that, and then let you go on with your talk. But
yeah,
it's just true that you can have quantum particles in angular momentum eigenstate. Yeah,
but
right?
No, but what happens
if you have an S wave, particle going out, then that's not localized anywhere on the horizon. So, and
sure, that's fine with me, and I'm fine with that. I agree that but like that there's no content or not enough content in the higher than S wave guys is what my question would be basically. Sorry, like.
Well, there,
like how much.
In general, the Hawking radiation is sort of dominated by the S wave. There is a significant component in L equals 1, 2, 3, et cetera. But anyway,
exactly. So significant is enough for me. That's why I mean, like I don't know. I need to talk with you more to figure out how insignificant or significant that fraction is. Sorry, like if that makes sense for what I need it for.
Please proceed.
I agree that S wave stuff is going to like is not what I'm studying here. So I agree with that. If you can justify that whatever's in here wouldn't be enough, then that's an issue. But I'm not convinced yet, maybe my own ignorance, but I'm not convinced yet that if you got rid of the S wave, that it still wouldn't be enough. I definitely don't want to claim it's everything right now. Yeah. Okay, so I'll move on for now, and then hopefully like some more questions will be sparked later on with when the assumptions about this like size of this Hilbert space, this part of the Hilbert space gets said. So what I'm pointing out at this stage right now is just that I can create these operator value coordinates, which are going to be super translation invariant. But this F that I have here can be any one of my F modes. So for now, I'm focusing on the soft hair associated with the horizon. But in practice, what you would you could still choose now the F plus or F minus. So I make the claim now that I want to dress my in observables with this F minus and my out observables with F plus. And right now there's a bit of I'm still choosing to describe things in terms of a metric that's been fixed in advanced Bondi gauge. And so that's why you see this non-symmetry in U versus V here. But this is going to be important. The second term is here because you're going to see then this fun commutation relation if I choose addressing that way. So what I want to argue basically in the next couple of slides is that the structure of the symplectic pairing between the early and late soft hair modes associated with the horizon gives rise to essentially like keeping track of the back reaction that one would have when one like probes with out of time ordered correlators, the dynamics of like how one shock wave falling in is causing a back reaction of the black hole horizon, which affects then the outgoing observer. So right now, what I'm just writing down here is the fact that if I'm near the horizon, the UV are like close to the horizon, then this term dominates in a possible bracket between U and V when this F and this F are the two different early and late zero modes. So what I get now is this exponential sensitivity here to the U and V as they approach the horizon, and just some definitions of, I guess, the constants pairing out front, and where else here? So then basically this angle dependence here is because the fact that like it just comes from the Green's functions that one gets when one looks at the brackets between the two F's as compared to the phase space structure for the full metric, where now F is parameterizing basically dz squared of F is HCZ. So there's some Green's function here, so it's not local on the S2, and you get this non-trivial commutation relation between my operator valued V coordinate for the dressing for the incoming state and the operator value U coordinate for the dressing for the outgoing state. And so given that, because I have my in and out operators basically being plane wave dependent on this V hat now and U hat now when they're dressed, I would get basically this reproduces the Lyapunov behavior just coming from the dressing here. So that's fun. So basically, the one thing interesting about this is essentially somehow the phase space structure associated with these soft modes at the horizon are capturing kind of like the back reaction effects. And so then one can define this stretched horizon as being the locus where that quantity is order 1, and one sees that from the point of view of two operators that are, say, coming in and propagating from past null infinity or propagating out to future null infinity, the region where their signals would become like of the order of the Planck scale here would be is basically shown in this dotted shaded region. For fun, I can do the same thing though if I look at two observables that are on trajectories falling in through the horizon, and doing so would cause basically this stretched horizon to recede into the interior. So let me see what so I have now basically to do this computation as opposed to the last one, I want to look at some trajectory that's falling in. So I parameterize it with U as a function of V and vice versa, inverse here. And now I dress with the proper time coordinate. And again, this proper time becomes operator valued with the dressing appropriate for inverses out that I'd claimed. And so you do the derivatives you need to do to evaluate the dependence on F hat. And one finds that now these blue shift factors are appearing here. So it matches the, I guess, the physical interpretation of just matching where if you send a signal in and you want it to be of order of a frequency set by the size of the black hole when you emit it or when you observe it, when they would interact, it would be blue shifted. And so this is capturing that blue shift factor. Good. Okay, so now I guess here is where things become more controversial. We can have some fun debating stuff. So the point of view that I made right now is that if I want to consider observables that are supposed to be invariant under super translations, because it's a gauge symmetry in the end, I need to dress them. And when I dress them, if I choose a certain anchoring of those dressing, that corresponds to the early versus late part of the phase space for this horizon soft mode, what I get is that I basically am seeing this back reaction, and I'm basically now trying to argue that once you have the structure where you have this sensitivity that you see in U and V, like which would be reminiscent of like some sort of chaotic dynamics, that this is signaling that I am very much entangled, as the observer is very much entangled with the value of F as they cross the horizon. So the claim that I want to make now is that by falling into the black hole, you're essentially making a measurement of F. And if I did so say I say that if I tell you exactly the soft hair of this black hole, or at least the part of the black hole that I'm able to probe by making observations of whatever coordinate system I've set up and fall through, is some large enough fraction of the actual Hilbert space of that black hole, then basically I would be jumping down in my entropy here and then resume the standard, I guess, Hawking evaporation process for the black hole after this observer has fallen through. So what I'm going to end up needing though is that the measurement of the soft mode is a significant fraction of the entropy of the black hole, and that's where I guess our discussion before was calling things into question. So we can debate that. But basically what I want to say now is that what I'm going to motivate in what follows is that say I am right in the end, that these soft modes do incorporate enough of the degrees of freedom of the black hole, then I'm going to try to promote a certain observer soft mode entanglement structure, as well as these different Hilbert space factors associated with these soft modes to provide this HPS interpretation of certain quantum teleportation arguments that have been used to avoid firewalls. So I want to show that the late time radiation is entangled with interior modes rather than the early radiation. So basically, like, we're going to try to plug in some definitions of these soft modes into Benny Yoshida's quantum circuit technology, and then use that argument to say that the horizon would remain smooth. So I'll present the argument, and then I'm happy to dissect it with anyone who's uncomfortable with certain parts of it, which is like this, because that's part of the good fun of giving a talk at UCSB, because you guys do this a lot. So okay, so great. So my claim is the following. So you have this soft sector of the phase space associated with a black hole, and I say that an observer who falls into the black hole is essentially measuring F. So now this FO is associated with the observer. So this is the full observer, and this OF basically is now, in some sense, I guess, state dependent. So OF, this little F here, is the projection of my rest observer onto a given soft sector with a definite profile of F. So now the claim that I want to do is I'm saying that for like this black hole that's basically at like page time, I will have this EPR pair between the observer's Hilbert space and the soft hair of the black hole. So let's see what that'll look like. Oh, one step before I draw that circuit is to actually just look at this black hole Hilbert space and clarify where this soft mode is coming in, and this is related to the question that was raised. So I want to claim that I can break down my black hole Hilbert space into a bunch of ones that are labeled by definite values of the soft hair, and so then we can argue if this soft hair is really large enough or not. But the claim will be that it is, and then we'll see what follows from that. So if we assume that basically once I've made a measurement and fixed the values of the soft hair mode around the horizon, then I'm on some code subspace. I'm not trying to argue that this code subspace is like one-dimensional or something like that. Like I can still be large, but we're gonna probably not necessarily as large as what you were suggesting though. So let's think about that. But basically now I'm going to say that this code subspace has some basis, and then the soft hair eigenstates are labeled by this F, which span this soft part of the Hilbert space, and I embed my this code subspace and this soft sector, which I guess is isomorphic for every different choice of F, into my black hole Hilbert space as follows. And so this embedding will basically take me from some state, if I've stripped off the soft hair, to the one in this full black hole Hilbert space on which the unitary evolution of the black hole will be considered to be scrambling. Good. Okay.
So maybe just a quick comment. So since that is maybe just to highlight, that's one point where the difference occurs
exactly
at a technical level. That those subspaces H sub F may be quite big, and that's the thing that we have to settle.
Yes. No. Exactly. I completely agree with. No. I completely agree. This is where things start getting hairy, or or not.
so.
Exactly. So I'm happy. I'm actually very happy to have the chance to talk about this with you guys, because So okay. So the claim is okay. So that's where things can go wrong, and what's going to follow next, especially because the way that I basically, there's some assumptions from like Benny's circuitry that I want to claim are true, and then if they're not, that's that's a problem. So okay, so right now in this first part, I've basically claimed that I've created this EPR pair between the observer and the soft part, like the soft Hilbert space of the black hole. So the soft hair is entangled with O, and then the whatever else is in the black hole is entangled with earlier radiation. And so what this looks like for me now is I've just basically taken this S and the C, embedded it into my black hole Hilbert space, and then evolved it now with something that's scrambling for a order the scrambling time. So I'm in this state now where I have my observer and it's entangled with the soft hair. That soft hair has been evolved with the rest, whatever is left over in the black hole unitarily, but in a scrambling manner, and produce some later, B is late radiation, and then the black hole state after that late radiation is emitted. And so now we want to see where this late time radiation is entangled with. So here is where the the thing would break down. So what I need is the following. I need this ds, so this is a soft, to be a lot larger than the dB. So, and we can maybe be a little bit more careful if we want to go back and check if there's any other assumptions about, right, so one could imagine that maybe that can still hold in certain contexts if you're only looking at a small amount of light radiation, but I would be worried about that. So technically for what follows, I believe this is the only assumption of the theorem by Yoshida. We need this soft dimension of the soft Hilbert space to be a lot larger than the dimension of the late radiation at the time where I'm drawing the circuit, to then construct this thing where we show that the B mode is entangled with what we want it to be. So, okay, so the claim here is the following. So if that is true, the late radiation and the early radiation would be decoupled. And so basically up to some error of order size of the late radiation and the soft space squared, it's a tensor product. So good, that would basically mean then that the late radiation could be entangled with the black hole still. So that would be the smooth horizon statement. So, and then we proceed following Benny Yoshida's work, but with this HPS interpretation, that we can produce these partner operators that are acting on the black hole and the observer without using any degrees of freedom from the early radiation. So I'll show a couple slides where basically now it's the same as used there, but now with this interpretation of each of the different tensor factors that are appearing. So we have our observable still, we have this code subspace here appearing, which is the question of how big is this compared to S, I guess is up in the air right now between me and you guys. S is the soft modes, it's appearing and so basically in the F dependence here. And I don't know if you guys can see. So then the important part here is that we've introduced at some point an Gonzalez space, but at the moment, this little b is our late time radiation. Goodness. On the right hand corner should give all of the answer keys for what each of the subscripts mean in this, but essentially we're saying that now you have this scrambling evolution described by these random ergodic cross operators, which is follows, and then we just go about saying that we can produce this recovery operator, which will distill the Hawking partners of the late time radiation. And so in the paper, we write down what these guys are. So hopefully I've also written them here. The R that's appearing in this recovery operator is written in terms of other cross operators, which basically undo the action of C. And so in like this nice quantum circuit notation, we've written down what this RF is. Hopefully I wrote it down. Yeah, write it down. That will implement what we want to. So at this stage, what I'm basically saying is that we have, for the assumptions that basically are going to define, like, so first of all, we have this entanglement structure that we try to motivate. We also have this assumption on the size of those different tensor factors, but then once we have that, we are basically applying this quantum circuit technology that Yoshida developed, and others, to make this argument about where the partner of B is. And so what we have now is we also can write explicitly using this R that I've shown how to construct here, write these mirror operators that are acting only on B and O. And for those guys, then you have this like thermophile double type entanglement structure, which is going to be consistent with no firewall. So I guess, so I'm going to say that we concluded and happy then to like delve into this a little bit deeper about what assumptions were not okay to do. But from my point of view, if I was happy with each of the the things that I said I motivated, then we would have examined the software phase space, explored entanglement, motivated this, and then the fourth thing, I guess, is the question of if the software phase space isn't large enough, you could wonder if 4 still holds. So I'm happy to debate that. So that's what I wanted to say, and let's go into any issues that you think we have, so we can see if we can come to a common ground with that.
Thank you, Sabrina, for the talk. Yeah, I guess we have quite a lot of time left, so we'll just open to questions.
I have a question. So in the plot you showed for S versus time, so
yeah.
Your claim is the shift is of order entropy of black hole. Is that the claim, or It's just
Oh,
order.
sorry. Oh, yeah. Yes.
There was a shift for S of soft.
Yes.
So is it?
Yes. So I'm claiming.
Mhm.
I think that I would basically want to claim that S soft is still order 1 compared to SBH, right? So now the question, here's the following question, is I don't want to claim that every time somebody falls through, they're making that full measurement of everything of the black hole. For instance, in the structure here, I would imagine that what I call C and what I call S would get shuffled around if, say, the observer was charged or the observer was spinning. I mean, maybe there's still some orbital angular momentum, but basically, if there's different soft hair modes associated with different gauge symmetries of the space-time, then I would imagine that there's some change here that's happening. For instance, if this black hole eventually evaporates and you follow this quasi-cyclically, at least both of these guys shrink with it, or assume this guy shrinks with it too. So, wait, so does that answer?
I mean, one thing I'm worried about is that you can have models that you have some large N matters like coupled to black hole and look at the H curve in that case. And then, I mean, it's kind of strange if like only soft modes of graviton is supposed to like solve the problem, because you know, there's just many fields. So I'm trying to see like what's exactly the statement, like
I mean, so this,
what
I mean, this,
they're gonna like solve, you know, Firewall Paradox.
So the question, I mean, maybe can we turn it into a question of what the observer is experiencing when falling through? Okay. So yeah, I guess the subtlety of if you have this actual like bath of things or something happening at the horizon, like then you're hit by that. That's not good. But from the point of view of like, so if, okay, so let's try to see where it would break down in the sense that if I am saying that that this quantum circuit technology exists, then somehow it makes sense that O is measuring like this soft part of the horizon as it's falling through, and at least that would yeah, no, I'm sorry. I definitely, so like basically the nice part of this type of intuition is that somehow by like setting up this frame of like your frame of reference is essentially like landing you on this like semi-classical geometry with a given value of S. So that's nice about it, but I agree, like I'm sidestepping the question that you're getting at, which is then why, for instance, why would this observer be like, why is everything in soft hair? Yeah, so if I could push, if someone were to tell me that like that Hawking period Strominger were right even in the more extreme version of what maybe some of them wouldn't say, which is that everything is encoded in soft hair, then I'd be fine. And then I could argue that whatever evolution's happening of the black hole is then putting everything you're worried about into the soft hair, and then I can be entangled with it because that's a semi-classical geometry I'm observing, and then my statement goes through. And then the reason why, for me, then the code subspace would be the part of S that you don't measure by the fact that you've fallen into one part of the black hole. So I think there's a part of me where I am kind of hoping that Hawking period Strominger are more right than even I'm using, because that makes my stuff safer versus like I sort of admitting that basically I want them to be right like in their information paradox thing, not just in yeah. So okay, so let's try to break it down into where things would go wrong here. So maybe does someone want to go into more detail about why they think that the software can't capture the stuff? Okay, we started talking a little bit about it, but let's revive that too.
Maybe sticking with the present question here.
Okay, no, sure. So yeah.
So I asked about getting all the information into the software, but on the measurement question.
Yeah.
So, let's suppose that somehow the information does get encoded in software. So I can have, say, a bit of the information encoded and presumably sort of one graviton's worth of soft hair. Soft hair is basically soft radiative modes of the gravitational field. So I could have one bit and roughly one quantum of soft hair. And then the question is, how well can I measure that if I fall into the black hole?
Yeah.
I would think that would be extremely unlikely to be measured, just if I think about it physically, by an observer falling into the black hole, just because that one graviton is so weakly coupled to everything.
So I want to fight that a little bit in the sense that, okay, so maybe I would revert to the way that Parati and others start talking about the null infinity version of things. So I agree. So if anything, I would say that the parts going under the horizon, there's fewer degrees of, like, there's fewer F, because you basically have this, this cutoff of the Planck scale, and you have this finite area surface. So like, if I try to specify F as a function of this horizon, I really am specifying less data at the horizon than I am at infinity. So I find
it's one quanta of F, so to speak. You know, suppose
I don't know. So I'm not sure if I want. Okay, so I'm not sure if I want to say that I only measure one quanta. What I mean is, what I'm trying to rely on is the following: is that if I said that I'm effectively measuring C at null infinity, say by setting up a set of rulers and like clocks, then I would think that I could still do that same thing at the horizon, because if anything, now there's fewer F associated with it. So in some sense, I guess what it's getting at is whether or not when you are basically setting up some sort of coordinate system to describe the region of space-time around you, whatever that would mean, like that the fact that I can send like signals back and forth, or like, I don't know, like how I basically like tell where things are in my vicinity as I'm falling through, like that's essentially picking an F for me. So I agree that it's a subtle point, and we can try to like to break it down a little bit more about what it would mean for me to experience the semi-classical geometry, and that's what we're getting at. But I agree that it's a little bit hard to make that more precise. So I want to say that in the same way that, say, Parati and others would say that I could set up a measurement of C at null infinity, I am basically doing that now as I fall through the horizon. So it's a funny statement, because in principle, what I'm doing is I'm saying that like this black hole itself could have all of these different soft hair states, but once I'm falling through, I'm basically measuring the classical geometry part, and that is described by the soft hair modes. So I agree that like I don't see quite now how I would say I'm measuring this in a qubit type like counting thing, or if I want to say one soft graviton, because for me, like how much can I measure when I like, I guess like shine a flashlight and like see my friend something somewhere, you know, like, I don't know the extent to which I'm like able to make a certain measurement.
Well,
Yeah.
but we have at least, and maybe this is wrong intuition somehow, but we have at least some intuition for this, and maybe there's something in the present story that gets us out of it. But the intuition is that we can have, you know, these absolutely massive gravitational waves that pass through Earth, and it's really, really, really hard to measure them, right? With
but it's not as hard to measure.
So,
but the memory effect is something that I measure. Sorry, so let's go to the infinity case, because so I send in these modes are very like a different type of measurement. So normally, if you would want to measure, say, let's do an experiment at CERN and not the gravitational version of it, but I guess that changes things, because like obviously the size of the coupling constant. But normally, if I have an energy position detector, it'd be very hard to measure soft modes. The way that the soft modes are measured instead are basically, so instead of looking at like the dynamics of what's happening, say, if my interferometer for LIGO, I'm looking at a net change of like my positions.
Yeah, well, which
so
is,
I can
LIGO does
see
something
that
like that, right?
Yeah. So, but I mean, but in the sense that this isn't like, I'm not trying to find the full waveform. I'm trying to just see this, what's imparted in the end, like this memory effect observable. Yeah. And it's a different type of detector setup, because it's really not like there's some energy threshold issue, which would make it hard to, I couldn't measure the deposition of these very soft modes, but I can see them from a different type of detector setup. Now, I'm not trying to then, like, obviously, right, like I don't think I'm going to give a satisfying answer to you, but I'm trying to at least set up the way that I'm seeing it, which is that if someone could tell you that it's impossible to measure IR physics because of the same arguments about like what you use for summing over like IR inclusive observables and something like that. Like, I've made a measure my detector, I really have to trace over all these soft modes that I've ignored because my detector has a threshold. I would argue I could measure those soft modes with a different type of detector, which is looking at displacements of things. So in that same spirit, then I might try to call into question if the spirit of the fact that it would be difficult to measure something like at arbitrary low energies because of my energy deposition detector, and I get around it with this different type of observable, I'm saying that maybe that's the same type of argument that's applied to like this notion of these soft hair modes being somehow like part of the semi-classical geometry around you, which is not quite the same type of experimental measurements setup, if that makes sense.
Yeah, no, I had in mind more, not the analogy with, say, soft photons, but just the analogy, well, just the incredible weakness of the gravitational coupling,
Yes.
which in practice is why it's so darn hard to measure
Yes.
gravitational waves with LIGO, basically.
Exactly,
It's
but
one way of
it
saying
would.
it.
It's not.
And
In
you have
some
to have a
sense, it's
really
not
massive
hard.
signal to actually measure anything, in effect.
I
'cause
no,
you-
I agree with that,
large
but I
number of
think that
gravitons.
there's something analogous to that issue, to the spirit of the fact that I might not be able to measure a lot of things with the gravitons, but amongst the these low energy modes, I can see the shift in my coordinates or something like somehow that there is something imparted in the space time that like I inherently measure by, I guess, anything where I mean like a dolphin with the sonar types. I don't like, I mean, basically like I'm always kind of looking at things coming at me, and there's a coordinate system I've set up in that way, and that's implicitly making some sort of measurement. I know I don't like just saying that because it's very ethereal, but there is a sense in which that type of detector is the best one to see that these like low energy observables were there, because like, you know, something was here and now it's further away from me. Like I not quite, I don't think I'm fully comfortable with that, but I mean, like, that's the spirit of this.
Okay.
Sorry, I have a question coming back to that. Even at null infinity, the soft modes can basically only be measured by waiting for an infinite amount of time.
Effectively, yes. No, and I agree with that aspect. So what I want to say is, though, for a given scattering process, if you break things up into like basically static patches, or say as far as if my detector is like, if I'm able to, I guess, look at what's happening with LIGO, say, like sorry, so my one interferometer and a given black hole and spiraling binary, I can deduce what that effect is, because basically I can add them all up. So I agree that in principle, measuring the full net memory effect is just about as impossible, because you wait forever to see it. But for a given impulse of radiation going through, and then assuming some sort of like nothing's happening for some range of time, no radiation for a while, then between those two different time frames, I basically measure a memory effect. Now, even though that doesn't resolve this issue of the fact that strictly it's a very IR observable and strictly I have to wait forever to see the full memory effect, I do still have this change that I've observed, and the metric at those two times would also have a similar type of bracket structure. So I could break my plus and F minus into an Fi labeled by the time intervals over which nothing's fallen through. That's not necessarily super ideal, but from the point of view of you, like imagine like nothing's been going on, something falls through, then something rings down, and then nothing's going on again. Like the fact that those zero modes wouldn't commute would give me the same structure that I have here. And also the fact that basically having passed some sort of shell of matter has shifted things around me is also something I can measure. So I'm extracting the low energy parts of whatever I've happened to come across in a finite amount of time, I would say.
Okay, so ideally, would sort of the soft modes saving, you know, firewalls or information loss also take infinite amount of time?
No, so that's what I'm starting to argue, that there is a part of the memory mode which isn't ideal. So it's not ideal in the sense that it's not, there's assumptions, I guess, going into the fact that like nothing special is happening for like, okay, so at let's do null infinity, because I am a bit of more of a soft physics null infinity person, so at least I can ground myself in those examples. Yeah. So if I say that there's some isolated scattering process, whatever's happening, and it emits radiation, and then that radiation has some sort of tail. This is a lot of assumptions going into that, right? Like I'm saying, if then I know that if I looked at the positions of my detectors, they will have moved by some amount. So what I want to argue is like there's a sense to which I am, like by tracking the positions of the detectors and then seeing that they're not moving after some time, I can define a memory-like observable just from the fact that I've seen something move apart. And for now, I've made a measurement of that, which means that basically I know what coordinate change I could do right now to reset my detector. And that's a statement I can make in finite time. The fact that there even exists, though, some region of time within which I can isolate one event from another is a different assumption. But what I mean to say, there's a sense in which I can subtract the effect of one given event coming through with a diffeomorphism now and basically reset my clocks and my my rulers, my grids say. So what that's hinting at is that somehow these IR parts of the metric are like, I guess the party line would be that that's that your ability to, like, I guess, measure positions of like objects around you relative to one another is intrinsically making a measurement of these IR modes, is what I would say.
Yeah, but I mean, I think Steve was pointing this out, is LIGO measures displacements of detectors all the time, but we don't claim that they've discovered the memory effect. I mean, they still have to do it.
No, they still have to do it, and they have to do that because they have to be able to separate out the signals. But they would, I mean, in some sense, they would measure that. Like, so LIGO in particular is, I guess, a bad example in the following sense. And this is where we can have some fun talking about ring downs or whatever, is that if I have detectors based on the ground and then I have this matter flexing through, they wouldn't normally measure the memory effect because, like, I think their mirrors are set up on, like, to basically restore to the same position. Right, because the issue with the one issue with the memory effect type thing is if you really did have an interferometer and the positions of it move, now every time after that, like, things are going to be in a different, like, phase because now they're moving a different distance, right? So for some situations, I think you'd prefer to have something restoring it. Once you have something restoring it, it's not really the memory effect, and that's why they have to do the extra work to see it. But I would say that if I had some freely floating test masses and I have something going through, and then at any given time I say, okay, whoa, I've moved a bit, now I know I'm stable again, or whatever that means. So matters pass through. If I look at the distance between me and my test mass near me, I could say that, like, our distances are now not changing with time below some given threshold of, like, how much is changing. And now look at the distance between us and make the same type of measurement I'm saying that you'd be making by measuring low energy observables near the horizon.
Yeah, I think we're agreeing that you can say low energy below some threshold, which is, you know, observed for some threshold of finite time. But the real soft modes are not low energy, they're zero energy.
Sure, but the issue is to, like, once you're, I feel it's a little bit, I'm trying to associate these observables with like basically the coordinate system that you're using when you're falling through the black hole. And I can always, in some sense,
all I'm pointing out is, you know, you're using some time scale to say, okay, now I have stopped moving. You know, my detectors have essentially stopped moving.
I agree with that.
Okay, so I think we agree on what the basic point is.
Yes, but you would see, you can definitely bound the size. Like, for instance, I agree that there's some cutoff in the sense that, like, what if there was a small amount of motion, you're not seeing it, and then you claim you're in a static state or something. But like you can always bound the fact that, like, I have a certain distance change, and you would notice if that were changing again. So like you are, like, I'm saying that there's a sense in which we're trying to claim that the coordinate system that you're setting up for the set of, like, objects around you as you're falling through, so, like, you're not just one point particle, you're somehow a frame around you, that's effectively making some sort of claim or measurement of the soft hair. Now, if you even wanted to say it's a gauge choice, like, say I say wherever that particle is, it's this is the distance between me, and call that, like, X. And I mean, like, sorry, like, there's a sense in which
yeah, you can just, like, say that the distance is 1 meters.
Yes, exactly, and that's that change that you'd be making is a super translation if you formally wanted to do that. Like, not saying, maybe not, like, just the definition being the meter, they're not in, so what I mean to say is, so what I'm trying to get at with the one point about the subtleties of the IR is, even though I know I could only really say to some precision that, like, the particle's distance isn't changing, I would have some sense in which, like, the amount over which it could change in a given amount of time would be, like, at some point I would see the difference. It's like, you know what I mean? So, like, there's a sense in which I'm still, like, effectively measuring some part of that IR, like, those IR observables, like measuring the fact that I have shifted by a measurable, right? Like, right, I mean, like, some things happen and then I say it's static, and I still say it's static. For as long as I say it's static, like, I tell you the shift of my coordinates, and that's not going to just arbitrarily change. The amount it's going to change is bounded by what I can or can't observe. So, like, there is some like I can use that information to then redefine my coordinates, do a diffeomorphism of it, and then like, I mean, I've captured something, I've still measured something is what I'm saying, sorry. Like
no, yeah, no, I think we are agreeing that,
yeah,
you know, if you wait for some decided amount of time scale and nothing happens, you can associate that basically with some IR kind of thing that fell in. Yeah.
So, but the claim that I have is that essentially the first time that you're setting your coordinate system is basically choosing C at infinity, and that when you keep that coordinate frame with you as you're moving through the horizon, that's projecting onto the coordinate frame for the horizon, which is the F. And maybe there's a precision with which you can do that. See, I would argue that there's a precision with which you can do that, as opposed to, like, for me, like maybe the fact that I am imprecise at infinity is related also to like how much, like, these are one of our effects still, right? So like there's a size of the celestial sphere within which I can basically gauge things as being like low energy, right? So if anything, I would have thought it would be easier to somehow measure the degrees of freedom in F associated with the horizon if there really is this UV cutoff, because I only need to measure now some sort of like plaquetting of the soft hair modes in some sense, right? Like, so I have the area divided by Planck length size areas, which tell me the value of F average over that basically is all I could hope to measure.
Yeah, so, I mean, yeah, I think the spatial size isn't actually the thing I was pointing out. It's that you have to look at the time scale.
No, I agree with that. What I mean to say, somehow the time scale is also associated with this spatial size in some sense, just because like my detectors are a certain distance apart.
Yeah, no,
like, they're interplaying with each other. So I would have thought that it might be easier. I'm trying to think about whether it would be easier or not if I'm near the horizon to control my coordinates because of that.
Yeah, in space you probably can, but in time, yeah, you'll have to set some time scale and then say, oh, now I'm static.
Sure.
Yeah, and yeah, I think that totally works. Okay, we're actually 15 minutes beyond time. So I'm going to stop the recording thing.
Sure, that's fine. Yeah.